Welcome back to Mathematical Maths. So today we're going to be doing the Taylor series expansion for sine x and cosine x. Now, a lot of you here may have already done this before, but just want a refresher, or may haven't have done it before and just want to see how it's done. So yeah, that's what we're going to go through today, and hopefully you can learn how to do some Taylor expansion. So we start off with a polynomial with n many terms. So we're going to have c plus bx plus ax squared plus, we'll call it zx cubed, and we can keep on going back. Now with Taylor series, what happens is the more terms you add to the polynomial, the better approximation you'll get for the function you're trying to mimic. So in this case, we're going to do the sine function. Now what happens is each one of these terms is responsible for a certain derivative. So the first one's going to be responsible for the y location. The b is going to be responsible for the first derivative, a second derivative, and z third derivative. So as we work through this, you can see that we're going to approximate it around the point 0. Because when you're doing Taylor expansions, you never approximate the whole function, it's around one particular point. And we can see this by the Maclaurin part, where we represent a sum from 0 to infinity with the derivative of the function n at point 0 multiplied by x to the power of n divided by n factorial. Now you'll see where we get the n factorial from, but the x to the n is from like these terms here in the polynomial. The f, the nth derivative of the function around the point 0 is how we get like the b, the a, the z, and then the n factorial is, well, we'll see. So when we're writing the sine function, we have sine of x. When we take the derivative of this, we get cosine of x. When we take the derivative of this, we get minus sine of x. And when we take the derivative of this, it's minus cosine of x. Now, since we're doing it around the point 0, we're going to plug in 0 for the x coordinate. So this will be equal to 0, this will be equal to 1, this will be equal to 0, this will be equal to minus 1. So now all we have to do is set each one of these terms and their counterparts in this polynomial to whatever the derivative is. Because after negative cosine of x, it goes back to sine of x. So we'll start off with c. When we have the sine function, we can automatically see the y location goes through the point 0, 0. So we can start by saying in this series, c is going to be 0. Now we're going to do the b term, and this is going to be the first derivative. Now because the first derivative is 1, we're going to say 1 equals, and then we take the derivative of b, x, and that just gives us b. So b is equal to 1, so we just have x. Now what we're going to do is we're going to do we're going to figure out what the a term, or the a coefficient is. So we're going to go here, that's 0. Now what happens with the factorial is we bring the 2 down in front, but then we take the second derivative and then we bring the 1 down in front. Because it goes from ax squared down to 2ax, then to 2, you could almost think it's 2 multiplied by 1 multiplied by a at that point. So that's what's happening, and that's where you get your factorials from. So here it's going to be 2 factorial multiplied by a, and in this case it's still equal to 0. So you can start to see that all of the all of the odd terms start to cancel out. This is why sine is considered an even function. So as we work through it, you'll see. So now we're going to put in the z, and we're going to figure out what the z coefficient is. So that's z, and then we bring the 3 down, 2 down, 1 down. So that's multiplied by 3 factorial, and this equals to negative 1. So z equals minus 1 over 3 factorial. So we can put this in here, plus x cubed divided by 3 factorial, and that's negative. Now, as we work through this, we'll start to see that, as I said, all of these even terms, all of these odd terms start to go to disappear. So what will happen is the signs, the respective signs will start to disappear. So the first derivative, the third derivative, fifth derivative, and on and on and on. So we can see here, well, since we're going to look at this function, x squared, x to the fourth, so what happens here is we know that this is going to be equal to sine 0. So we can do the same thing again, or we can just say, well, we know a 0 is going to equal 4 factorial multiplied by whatever the coefficient is, so it's going to be 0. Now we're going to work with the next one, and that's positive, because we're back to this cosine. This is going to be x to the fifth divided by 5 factorial. And as you can see, this just continues and continues. So that's why sine is an odd function. Sorry about that. So because it's going from 1, 3, 5, and on and on and on. So when we represent this, we can get rid of these terms here, and we'll be left with x plus x to the third over 3 factorial minus, and then that's going to be x to the fifth divided by 5 factorial. And you can probably see the pattern now. It's going to be plus x to the 7th over 7 factorial minus x to the 9th over 9 factorial, and then it's going to go to 11, x to the 11th over 11 factorial. Because that's 1 to 3, that's 2, then to 5, that's 2, 7 to 9 to 11, 2. So what we're going to, and this is going to be positive, because it goes positive, negative, positive, negative, positive, negative. Excuse me, positive, negative. So now we need to figure out a sum that represents this term, because we have a polynomial now that represents the sine function. So now all we have to do is expand this, or represent this as a sum term. So this is from n equals 0 to infinity. So what's going to happen is we can say, well, we know it's going to be alternating, and it's almost like a harmonic. So it's going positive, negative, positive, negative. So we know we're going to have a negative 1 in there somewhere. And if we raise that to the nth power, well, let's see what happens. 0 to the power of, or n minus 1 to the power of 0 is 1, and that's positive. Then to the power of 1 is negative, 2 positive, 3 negative, 4 positive, 5 negative. So you can see here we've automatically matched, or like shown that this is a harmonic series. Now we have to deal with the exponential terms. So we're going to multiply this by x to the power, okay, it goes 1, 3, 5, 7, 9, 11. So we know it's going up 2 each time, so we'll say 2n, but then it starts off at the first one, so it's going to be plus 1. So this term here is 2n plus 1, so x to the power of 2n plus 1. Finally, we're going to do over, now we just have to deal with the factorials, and the good thing is this is exactly the same as the exponential values, so we just need to put in 2n plus 1 factorial, and this, as it approaches infinity, will equal sine x. So we can say that. Now what we're going to do is the cosine function. Hi. Now when dealing with the cosine function, it's almost exactly the same as when you're dealing with the sine function, except it's just going to be a bit out of phase, and that can be represented by a plus 1 or minus 1 in this case. So when we have the cosine, it's going to be, as we know, the exact same as the sine. So we'll get rid of this just so it's a bit more clear. We'll put sine here. So this is how the derivatives are going to go. It's going to go 1, 0, minus 1, 0. So you can probably guess that because the sine went from is an odd term, because it was going 1, 3, 5, 7, and this has been shifted by 1, we can guess that cosine is an even function, and this happens to be true. So what's going to happen is we're going to have the same thing, a polynomial, so that's going to be ax squared plus bx plus c, and then we'll add some extra terms, plus z to the x to the third, plus w to the x to the fourth, plus q to the x to the fifth, and we'll go one more, and plus r to the x to the sixth. Now it's the exact same process. So we'll start off here, so the function. So we start off with 0, so c is going to be 1, and we can agree with this, because if we have a cosine wave, we can see that it goes through 1, and that represents the y location. So we're going to have 1. Now we have to deal with the bx. So we know from last time, bring 1 to the front, 1 factorial multiplied by b, or b, and that will equal 0. So in this case, we're going to get rid of this, but we'll just represent it as 0x for now. Now we're going to go to the ax squared 2 factorial multiplied by a. I'm going to skip over the explanations because I think you should have got this by now. So this is going to be minus 1 over 2 factorial. So that's going to be squared over 2 factorial. Now we're going to go to the third term, and I'm pretty sure you know what's happening here now. Z equals, that's back to 0, that gets z equals 0, so that's 0, and then x to the third. And then when we go to the fourth term, bring 4 down in front, so that's 4 factorial. And as we know, it's going positive, negative, so that's just going to be positive this time. That cancels out. And this one's going to be minus 6 factorial. That's going to be over x to the sixth. Okay, so we're going from, so these terms here get cancelled out because they are odd. So this is considered an even function. So we're going from x to the power of 0 to x to the power of 2, x to the power of 4, and x to the power of 6. And it's going positive, negative, positive, negative. And as we know, that's harmonic, just like the sine function up there. So we're going to have a negative 1 when we're representing it as a Taylor series. So we're going to have the sum, again, from n equals 1, 0 to infinity, negative 1, because we're going to have that harmonic or oscillation. And we start off with positive, so it's the exact same as sine, positive, negative, negative. Negative 1 to the power of 0, 1, positive, negative 1 to the power of 1, negative, minus 1. So we've dealt with that. Now you have to deal with the x term, multiplied by x to the power of, now what's happening here is, because it's going up in powers of 2, very exactly like the sine function, we'll put it to 2n. But because it's starting from x to the 0, you don't need to add that plus 1. So first term, x to the power of 2 multiplied by 0, 0, so that's 1. That cancels that out, and it's going to be over. And anyway, as we go up, that's going to be 1, x to the power of 2 multiplied by 1, x to the power of 2, and you can see where that comes from. Finally, we need to deal with the factorial, and lucky for us, it's exactly the same as the cosine wave. The exponential value is the exact same as the factorial, so we just put in 2n factorial. Now will equal cosine as it approaches infinity. So I hope this video's helped, and we'll do a bit more in the next video, such as we'll go into what the Taylor series for e to the power of x is and e to the power of ax. We'll see how that relates to something called Euler's identity, which is e to the I pi equals minus 1. It's a very, very cool function relating all the big boy numbers. So thank you for watching, and I'll see you next time.